I'm Professor Valeev, and I will talk to you for the next day and a half about computer architecture, algorithms, data structures, and things like that. Now, some of you may already know quite a bit of the material that's in it. As far as I understand, there's a significant variation. How many of you have taken anything but the very basic computer science class? Anyone here has taken like data structures? Okay, how many people have taken a programming class? Wow, quite a few. What was the language of choice, I guess? Java. Wow. Okay. Did anyone learn in BASIC? No? Okay. Oh, okay. I see. So, C? Anyone in C? C++? Fortran? Really? Okay. Okay, well, this is a typical makeup. I just want to make sure that I'm talking to the right audience. You guys are computational scientists. I'm one of you. I never took any classes. I learned by example. Unfortunately, the examples were bad. So you're lucky that you're in this group, because hopefully we'll show you good examples. Now, I cannot promise that all examples are going to be good, but this is a start. So I'm going to try to compress a few semesters worth of computer science into this. Obviously, it's not possible to do, but it's just to get some lingo into your head and also give you some idea of what is important and what's not. Because if you take an average computer science class, they're going to teach you like computer scientists. A lot of stuff that computer scientists care about, we don't care about as much. But today we're going to try to pretend like we are computer scientists. And let me start out by talking about why we need to learn HPC. Why you're here. Obviously, you have different motivations to be here. Some of you were told you were coming to this school, and some really wanted to come to this school. Nevertheless, hopefully, you will leave by saying this was a good thing. So I'll talk to you about why we need to learn HPC, and then we'll go way back and start talking about machines that essentially don't exist anymore. Serial processors. It turns out that there's a lot of technology that is part of the processor that you're dealing with nowadays that really goes back to things that were done back in the 80s. So we'll talk about serial processor and how they can run so fast. They can do billions of calculations per second, and they do some really crazy things. And we'll look behind the scenes at what those crazy things happen. We'll talk about vector processors because really nowadays this is a hot thing. This is an old technology, vector processors. They originally used to be, essentially all the supercomputers in the world were vector machines. And then they fell out of favor in favor of scalar machines or superscalar machines, partially because workstations were so much cheaper than time on a big great supercomputer. But nowadays, it turns out this technology is back. We'll see part of the reasons why this technology is back, why vectorization is the #1 thing everyone needs to worry about nowadays. And then we'll talk a little bit about parallelism. You're going to have several days of lectures on parallelism, parallel programming models, and so on. So we'll only talk about architectural aspects of it, not programming aspects of it. And then I'll summarize, and then we'll have a coffee break. Okay, so this is an overview of the scope of hardware that at least people in my group at Virginia Tech have access to. Well, this is my lab, okay? So I have a 4-processor machine. The vast majority of you have machines that have at least 2 cores. Maybe some of you have 4 cores. Does anyone have a single-core machine here? Precisely what I thought. And even if you think you have a single-core machine, it's likely not, because it probably has a GPU that has many cores on it also. This is actually I'm not really sure if this is up to date, but I have 24 GPU cores and 4 CPU cores in my machine. So it's already the scope of a supercomputer of maybe 20 years ago. In my office we have a bigger monster. It's got 12 CPU cores and 56 GPU cores. In our department we have something on the order of 1,000 CPU cores. We don't have GPU cards in this machine. The machine that you have access to is part of our campus computing facility. And specific machine that you have access to, the Hokie Speed, it has a bunch of GPU cards in it, but also it has a lot of CPU cores. And there's a machine that, Blue Ridge machine, the biggest one, has about 5,000 CPU cores. This is this is still a #1 machine in the world as of last top 500 list. This is Titan at Oak Ridge National Lab. And it has something on the order of combined, say, roughly 1 million cores. Okay, so this is a huge scope of computing power. Programming this machine and programming this machine, they have a lot of common, but they have a lot of differences. You'll learn about differences later on. I will focus primarily on inside a single machine. This is, you can think of this as a bunch of boxes like this. You can also project where this is going. It's clear that engineers have run out of ideas for how to make a single processor faster. Now, it's going to become faster simply because technology for making processors, for making silicon devices, is improving. The feature size becoming smaller and smaller, so you can pack more transistors. But those transistors sort of increase your power horizontally, not vertically. You essentially get more and more cores packed into the same piece of silicon. So essentially the machines that you're going to have, even a simple cluster nowadays can have easily, say, 1,000 cores. Well, it's going to have 10,000 cores. With GPU cards, it might have 100,000 cores. Okay? And you're going to be the one programming it, or at least you're supposed to be competent enough to know when to try to write code that really sits close to the iron, or when to find a library that implements an algorithm that you want for you. This hardware that is going to be there, you could say, well, maybe things will change again. Back in the 90s, we programmed for serial machines, and we didn't have to do anything in order for our codes to become faster. We wanted to run a calculation twice as fast, all we had to do was wait a couple of years. Then buy a machine for the same amount of money, but it would be twice as fast. Well, the party's over. Now you actually have to, in order to run twice as fast, you need to use at least twice as many cores, maybe more, because with time, performance of each core may actually drop. Okay? We'll see why. All right, so let's talk about processor families. Now, again, I don't want you to become a computer scientist. You don't need to be a computer scientist, but in order to be competent, you need to realize what it is that you're dealing with. Okay, so vast majority of us have machines here that use x86 processor family in them, besides GPUs. It may not always be this way. It may change. Maybe we'll deal with a non-x86 architecture, but that's what we're dealing with nowadays. So this is state of the art from Intel. I made these slides in 2012, so I'm not actually sure if AMD's architecture is up to date. But Intel's architecture, the last release was in 2011, and Haswell is coming out this year, which is a new architecture. But roughly, state of the art is something like on the order of 8 cores per socket. You can have multiple sockets in the same box. So we're talking about on the order of a few dozen cores within a box. Okay? Obviously there is generation switch in Intel case roughly every 2 years, and AMD tries to follow up. And all of this goes back to the Intel 8086, which was a 16-bit one core back in 1978. for various commercial reasons primarily, the code that ran on this machine can still run on this machine. It's a good thing in a vacuum. It means that a lot of the transistors here, they have to implement the instructions that were good at the time for running on this guy, but not nowadays. It's unlikely that the clean break is going to happen, but what happens eventually is Intel keeps adding new and new instructions that really can only run well on these machines, and they will not run on older machines. You will see that when we talk about compiler switches and so on. What about non-x86? You do have to deal with that. Some of you will have to deal with that in your career as a graduate student. The most important one is probably PowerPC. If you're ever going to find yourself running code on an IBM Blue Gene series, that's what's inside of them. Now this is a different architecture. It's very different. It's a very different set. In the computer terminology of, I guess, yesterday or yesteryear, this is a RISC architecture where the x86 can be viewed as a CISC architecture. RISC is a reduced instruction set, means simple instructions. In order to do something complicated, you have to issue many instructions, whereas in x86, each instruction can do quite complicated things. But anyway, PowerPC goes way back. Again, it's not really owned by IBM, but nevertheless, it's typically more power efficient than x86. Again, because the instruction set is different. The instructions themselves are simpler. You need fewer transistors, means less power needed to execute this. That's why they use this in IBM Blue Gene. If you look at the top 500 list, there's a counterpart called Green 500 that measures power efficiency. Well, it turns out IBM Blue Gene machines almost always end up near the top, even though they don't use GPU technology, but simply because the instruction set that they use is so much, takes less power to execute. Now, if you have an iPhone, if you have an iPad, you have something like this in here. It's a member of a different instruction set family called ARM. Okay? These are essentially king of the mobile space right now, even though Intel is trying to bring x86 technology to the mobile space as well, so we'll see. But maybe ARM will win, and maybe 10 years from now, we're going to be computing, we're going to be buying laptops with ARM in it, which will run off of half a watt of power or something like that. Hopefully not, but we'll see. If you are lucky to have an account on the K-computer in Japan, which was #1 for several years, it actually uses a yet different non-x86 instruction set. In the family of the processors called SPARC, instruction set is different, program obviously is different, and so on. Yet another one, and then GPUs, yet another instruction set underneath, nothing like x86, and so on. So that pretty much covers it. There are some things that I may have missed. These are minor players in supercomputing except for PowerPC. PowerPC is important. Okay, now let's talk about now sort of the big picture. Some of these names you may have heard. Okay, IBM Blue Gene series is just a series, a family of supercomputers. They had different generations. These are PowerPC-based supercomputers. They have proprietary IBM interconnects. There's one, it's a top 5 machine at Argonne called Mira. It's a 10 petaflop machine, so it's an IBM Blue Gene machine. The #1 machine, Titan, that's a Cray machine, that's an x86-based machine with GPUs. And the reason it needs GPUs is building a machine of that scope out of x86 would be prohibitively expensive. This is a machine, again, based on regular CPUs, special architecture, SPARC 64 from Fujitsu. And then generic, that's what we're going to be dealing with today. Just a sort of non-brand name cluster. You can build one yourself if you spend a little bit of money. You can easily buy a rack for something like maybe $100,000 or less. It's just generic x86 boxes with Linux running on it. Interconnect nowadays is very cheap InfiniBand technology. I'm not going to talk too much about interconnect technologies. And you can even stuff some GPUs into them. And that's pretty much bread and butter of HPC in computational chemistry. Okay, so we have all these powerful computers. Why do we need to know something about HPC? Can't we just say, all I need is publish a few papers, get my PhD, and get out of here, right? In order to do that, you have to publish some papers. That means you need to implement some algorithms that implement some novel computational procedure. Well, you could say there are these really thick books. They have a lot of algorithms in them. Isn't that enough? Well, you can go and let's say you need to solve a system of linear equations. There is CAN software for this. Now, if you want to implement, say, a nonlinear system, there's likely not going to be CAN software that you can use. But you can go to this book and look up a bunch of recipes for how to do nonlinear optimization or solving nonlinear equations. You can even program it, but is the code going to run well on the hardware that I've described to you? Likely not, without you understanding, actually, what it takes to take the simple code, and believe me, the code that's in numerical recipes is going to be just vanilla. It's going to be highly non-optimized. And you can optimize it by orders of magnitude by understanding something about the HPC. So that's one of the reasons. Another reason is pragmatic. You never know whether you're going to end up working with computers after you get out of graduate school or not. Some of you may go into academia and you hire graduate students, and then they do all the programming for you, and you don't need to know that. Or you get hired by Google and make 6 figures out of graduate school, and they're not going to hire you unless you actually only know how to read someone else's program and implement it. Okay, so 2 reasons. Plus, also, computers are changing. So really, you always have to be learning. Whatever I learned when I was a graduate student, it's still somewhat useful, but I always have to constantly keep relearning because things are always changing. A scary fact, we actually are nowadays probably using about 5% of the power of the computer. Now, is it a good thing or a bad thing? Well, I think the good thing is there's room for you to improve it. Lots of algorithms, they just need to be vectorized much better. But that may involve rewriting the code completely. And some of you are going to spend time doing this in your graduate career. If you came in, there is some existing code and maybe prototype, you're going to have, it may be easier to rewrite it. The situation will become worse with time. As I said, the computers are becoming bigger and bigger. You want to harness parallelism. I think nowadays it's actually less of an issue trying to convince people that parallel programming is actually important. But believe me, 4 years ago people said, there will be some library that I can link into, and it's going to make my software run on a parallel machine. And for certain types of applications, that might be true, but there are very few of them. Okay? Also, what I found is when you write even prototype code in parallel fashion, you can investigate new ideas faster, which for us, scientists, is actually important because we're trying to play around with unknown algorithms and figure out what we can do. And even if you write really crappy code, you can actually treat realistic systems if the code is parallelized, whereas a pilot and serial code may not be able to. Lots of reasons to harness parallelism and learn HPC. All right, now let's go back. Let's talk about how the computers do what they do. So this is an idealized model of a serial processor. It's pretty close to essentially idealization of it that Turing came up with. A Turing machine, a universal a universal computer, I guess. So we have some execution unit. We don't need to worry about how it does things that it does. But bottom line is it can follow instructions, and those instructions tell it to do something on the data. The data is organized into, let's say, typically one-dimensional array, so that we have addresses within that array, so we can random access any memory location we want. So these instructions can say, let's say, take data from D3, read it in, take data from D5, read it in, add them together, and write them to some other location. Okay? That's how literally it happens. So let's say here's an instruction, here's another instruction, and so on. In a serial machine, these instructions are read one at a time, and they're retired one at a time, and we can even think of this as they're executed one at a time. In other words, this guy can only work on one instruction at a time. In fact, we'll see in every processor actually has several instructions being executed at the same time. Now, each instruction here is going to act on one set of data. So let's think of this data here as being bytes or integers or floats or whatever you want, as long as the processor knows how to perform these instructions. The nature of the data is irrelevant. Okay. Now, let's talk about a slightly different model, a data parallel processor. What this processor is going to do is, instead of doing one instruction where each instruction touches one set of data or involves one set of data, now each instruction is going to act on several sets of data. In this example, it's two sets of data. So instruction 1 basically says, do an addition of two numbers. Now in this case, also you will notice that the addition touches the memory locations that are next to one another. Okay? So plus will touch D6 and D7, and it will add the contents of those addresses to the contents of D3 and D4. So one instruction processes two sets of data and produces a set of two results. So whenever we have single instruction that deals with multiple data, this is what we're going to call a single instruction multiple data paradigm, or SIMD paradigm. And whenever I say vector or vectorization, partially that's what I meant. And that's what I mean. Nowadays, vectorization means SIMD type vectorization. You can view this as instructions acting not on a single numbers, but vectors of numbers. Right? Most processors of today and all processors of tomorrow are going to involve instructions that do this. They include capability that will do SIMD. In fact, in order to get the top performance out of them, you will want to write your code such that SIMD type instructions can be generated by the compiler. Okay, now we've introduced data parallelism. Now let's talk about instruction parallelism, or task parallelism. Now here, instead of having a single execution unit, we're going to have multiple execution units, in this case 2. And each of them is going to receive its own instruction set, or stream. So technically these instructions are located in memory somewhere. I've separated them from the two because it would be a little too complicated to really explain in reality what happens. But bottom line is, think each of them is fed its own stream of instructions. The instructions are independent of one another. And so therefore you can retire several instructions or execute several instructions at a time. So whenever we say we have multiple cores in a machine, we typically mean this. In fact, even if we have a single core, we can have multiple execution units within that core that can all execute several instructions at a time out of the same stream. Okay, so This type of paradigm where we have multiple instructions and each acting as multiple data, that's a MIMD paradigm. That's essentially anything outside of the single core. All processors of today and tomorrow, as I mentioned, every processor has more than one core, but even if it had one core within one core, it already does something like this. It has multiple instructions executed at the same time. Okay, so the challenges of parallel computing. They can be classified according to the type of execution model we're dealing with. In MIMD, in multiple instruction, multiple data, imagine what happens when we subdivide our instructions unevenly. We're going to have a longer stream that the processor 1 or execution unit 1 receives than execution unit 2. Then execution unit 2 may actually run out of instructions to execute. It's called load imbalance. We're loading it with work, but we want to subdivide that work in such a way that both execution units are busy. Load balancing is a big issue, especially when you're talking about parallel machines with a lot of execution units, lots of cores, think that. Strictly speaking, in the limit of parallelization, when you really spread out your work in the most extreme way possible, let's say I'm trying to run an STO3G Hartree-Fock calculation on an IBM Blue Gene Q at Argonne with 1 million cores. Basically, it's going to, by definition, I don't have enough units of work. I don't have enough instructions in the entire calculation to keep everyone busy. So, in the limit of strong scaling, in the limit of really trying to parallelize, really trying to push the parallelism, you're going to deal with this load imbalance. Load balancing is a significant issue. Another issue. Let's say we have 2 instructions that try to access the same location. Now, if by accessing I mean reading, that's okay. If both of them are trying to read the same location, it's not a problem. But what if one of them is trying to read, the other one is trying to write? Well, that can be a problem. And it depends on the order in which these, I guess the timeline of these events happen. They happen roughly at the same time. You may actually get unpredictable results. Okay? So that's called data race. When multiple workers access the same data and at least one accesses a write, the result is, in general, not guaranteed by any architecture. It's unpredictable. And we say there's a data race. Dealing with data races is a major issue in designing algorithms for MIMD-type parallelism. And also, another issue is non-deterministic execution. It's hard to reason about multiple instruction sets happening at the same time. Because you will run the same program 10 different times and you get 10 different ways, sequences or timelines of how the instructions got executed. It can be very difficult to reason. All right, what about SIMD? Now, SIMD is a little simpler because the parallelism is much tighter in a sense. I mean, you know that basically you have one instruction and it accesses the adjacent memory locations. What is important there is the organization of data. In order to make SIMD possible, the instructions in SIMD must, in practice, work on vectors of data. And that means, in this case, we're adding these 2 vectors, D3, D4, and D6, D7. And they have to be next to one another. That means you have to organize your data layout in your algorithm in such a way that the data access is suitable for SIMD parallelization. And that's a major issue, and that's actually why we're running at such a low efficiency nowadays. Okay, so programming parallel computers is the main focus of the entire school here, although you have learned some basics of just day-to-day stuff. But let's, as I mentioned, we're going to try to understand how a computer works, a single core works, at a deeper level in order to understand a single core performance before we worry about parallelism. right, so let's go back now to the model of the simplified serial processor. So as I mentioned, we have instructions and we have data. Now data obviously sits in memory somewhere. Where do the instructions come from? They also come from memory. They're read from memory by a separate sort of stream, a separate channel, and those memory locations have to be read in and got to the processor in order for the processor to execute. And then there's the CPU, which has the execution unit on it. Now typically, whenever we say memory, some of the memory can sit on the same silicon as the CPU, and that's important because the closer two pieces of silicon are, the closer two devices are, the faster and the less time it may take to stream the data from one to the other. But obviously, a lot of memory is going to be separate from the CPU. Even though it sits in the same box, it may have a different location. So this gives rise to the memory hierarchy. This is probably the most important concept for the performance. We have different types of memory. In this model, we have an abstract model of memory, and this is what happens in reality. And the reason why we have a hierarchy is essentially, well, there are two reasons: physics and cost. Physics, because you cannot fit 20 terabytes of memory on a single piece of silicon. We simply cannot put this many transistors onto that piece of silicon and provide yields from a factory so that you have at least 50% of piece of silicon that comes out of it is actually usable. I mean, the yields nowadays, the yield management is an issue, right? I mean, so what if you can build, in a lab, one item that has, 20 terabytes of memory on the same piece of silicon, but in production environment, 99% of the time, you would have a flaw somewhere on it. That's not acceptable. So it's really the price and the physics, the cost and the physics. The fastest memory are the registers, and it's by far the smallest piece of memory. On modern machines, in order for instruction to be executable by CPU, the data for that instruction must be in the register. That's what I was saying, RISC consists. Some of you may have heard that nomenclature. There used to be machines that could actually operate directly on different memory parts of the memory hierarchy. Nowadays, pretty much the data has to be brought into the memory, and it has to be acted on there, and into the registers. There are only roughly 1,000 bytes. Now, don't take this literally 1,000 bytes. It's on the order of 1,000 bytes. So, how many numbers does that mean? How many numbers can we hold in registers at the same time? Well, in order to do that, we need to recall how many bytes of storage we need to represent a number. Now, to represent an ASCII character, we only need 1 byte, right? That's character type in C or C++. In order to represent an integer, standard integer, we need 4 bytes. So we're dealing with about 250 integer registers. Double precision floating point numbers. That's probably the most common type you're going to use. Though sometimes floats are okay. So there are really two main floating point formats that you're going to encounter. Float, or 4-byte wide floating point number, and an 8-byte wide, or a double precision relative to the 4-byte. Okay, so a float is a 4-byte wide double, and a double is float is a 4-byte wide real number, and double is an 8-byte wide number. So if we're talking about 8, then we have 128 registers. It turns out most of them are actually not directly addressable, but never mind. Roughly you have on the order of 100 numbers that you can store in registers. So if your data deals with 1 million numbers, they have to be sitting somewhere else. The next cheapest the next fastest, I guess, type of memory is so-called level 1 cache. It always sits on the die, and it typically sits right next to the core. If you have a multi-core device, then each core is typically going to have its own L1 cache. Notice as we go down the memory hierarchy, the size increases, but this number latency increases. What is latency? How long it takes to access. How long the delay between you turning the faucet on and the water actually showing up out of the faucet. Right? It doesn't come out immediately. So you send the signal and say, I want to bring in the number from L1 cache to the register. Well, it takes about 3 cycles for the processor to be able to act on it. Now 3 is okay. How long is a cycle? Let's think about that. Some of you have laptops open, and some of them are Macs, and so there's system information in there somewhere. So the number 1 out of that is the clock frequency. Different parts of the processor, different part of the machine are going to run at different frequencies, but that frequency is the clock that feeds the processor, not necessarily the memory. So let me guess, it's about 2 gigahertz, depending on how much money your advisor or you spend. I'd say mine is 2.7. So roughly 2.5 gigahertz. So that means you have 2.5 billion ticks every second, so it's 1 over 2.5 billion. Right? So it's sub-nanosecond. It's 0.4 nanosecond. Did I do the math right? Yeah? No? 0.4?
Yeah.
You guys aren't sure. It seems very short, right? Well, that's how, I mean, yes, how you realize. It's pretty fast. Okay, so this is still fast. Even though ideally you'd have 1, right? But this costs something like on the order of $1 million per gigabyte or something like that. So you can't have registers. All right, level 2 cache. Typically, you're going to have much more level 2 cache, and typically nowadays it sits on die. There used to be machines that had level 2 cache off die, but that was a long time ago. And it can be as large as 12 megabytes. In a server-type processor, typically it's going to be on the order of, say, sub-megabyte, and it can be shared between cores, or it can be assigned to individual cores. Typically, it's shared. Okay. Again, latency is higher, even though it's still not that bad. Level 3 cache, server machines definitely have it, and they're gonna have it typically on die. I'm not really sure where it is on a laptop. But bottom line is, it really doesn't matter. I mean, I guess you see that the progression here. Eventually, memory goes off die. Off die means off the piece of silicon on which the actual core transistors sit. All right, so it's about a few megabytes. So let's say if I have an array of million numbers, can I fit it into a level 2 cache? Typically not. 1 million floating point numbers, 8 bytes per number, it's 8 megabytes. Okay? So it's typically going to end up somewhere at level 3. Main memory, oh, these numbers are out of date. I don't think there's a machine nowadays with 256 megabytes of RAM. And what's the smallest laptop that we guys have? What's the largest laptop that we have? Who's the most proud? How much memory? 8? Yeah. I think there are laptops, I guess you can get up to 16 or so on a Mac. I'm not really sure about a PC. How many do I have? Actually, no. I've got to switch out. Something on the order of 8 gigabytes. And typically it's going to be several DIMMs. And we're going to see that actually it's not a flat memory either. It's not a flat memory anymore. Then disk, terabyte is dirt cheap nowadays, something like $100. If you want solid-state storage. It will cost you a bit more, maybe 250, but still, it's fast and cheap. Notice the latency. There's a huge latency bump up when you go to disk. Now, SSD is better, but still, latency actually is not particularly great. And then tape, that's just for archiving stuff. It can take, seconds for the robot arm to find the tape and so on. So obviously this is all logged down. All right, so why does this matter? I mentioned this is the most important stuff. You need to understand that in order for numbers to be usable, in order for an algorithm to be executed by the processor, the data has to flow all the way to the registers. Then the instructions occur, and then the result will go down. And hopefully it will hang in here for a while, and we'll see what caches do about that. But hopefully it will hang in there for a while so that you don't have to go that. Next time you access that memory location, it has to go all the way back up. Managing memory is going to be your job. All right, caches. A little bit about cache structures. Well, I guess the idea of a cache is, storing copy of something, right? Okay, that's essentially what caches are. They're essentially copies of what's held somewhere in the main memory. They don't hold the memory that is not in the main memory. They can only hold the memory that corresponds to some memory location in the main RAM. Now, they may contain a more recent version of that data that will be synced up somehow, but they cannot, there's no location in cache somewhere that will never end up in the main memory. Okay, so how does the mapping between the cache and the main memory occur? Well, there are different ways you can do this. Now, most of the time, you really don't need to know exactly how this works. The most important thing is to understand that the main memory is not just one linear array. You view the main memory as composed of blocks of memory that are called cache lines, that will become lines of cache. And cache can be viewed as a table. The width of each row in that table is characteristic of a machine. Each row is the cache line. Think of that as a unit of exchange between the cache and the memory. If you want to read one number out of random memory location, somewhere in memory, and there's some mechanism, some magic happening, you determine the address, you figure out where that is, on which DIM it is, and then you want to send that. Is that the only piece of memory that's going to end up in cache? No. Basically, it determines not the just exact memory location, but the cache line on which it sits in the main memory, and then it brings that line into the cache. So a cache line is the unit of exchange between the memory and the cache. And the width of it typically something like 64 byte on Sandy Bridge. I don't know what it is on Haswell, but it will differ, but it's roughly speaking a few numbers, a few floating point numbers, right? This is 8 double precision numbers. So if you want to read one, well, 8 of them are going to end up in cache. So what does that mean? It's better to optimize or write our program in such a way that all of those 8 numbers that we had to spend all of that power and energy to bring up to the level 1 cache, they better be all used. If only one of them is used, you've wasted 7/8 of the memory bandwidth. Okay, now how does this mapping occur? It's a little complicated. Basically, you have a table, and this table basically says which memory location which line corresponds to. That's the tag. Okay, so reading the data involves the following steps. You basically determine the address in the main memory. Then you figure out, okay, what is the tag of that line? You search, in the set of tags that you have currently in cache. And if you haven't found the tag corresponding to that line, that means that line is not in cache. If you found it, the data is in cache, you just read it directly from cache. If not there, what we call is a cache miss occurred. A cache miss is a bad thing because basically it means now the main memory actually has to get involved. It has to start, we have to read in the corresponding line from the main memory into the cache, update the table in the cache. Now, typically the cache is going to be full. In a real application that uses quite a bit of memory, I mean, the caches are small, so you're going to have already a whole bunch of lines in there. So there's going to be some heuristic algorithm that will decide who of them is the bad guy and needs to go. Okay, so that's the eviction algorithm. It's typically some heuristics, least recently used or something like that, basically. So that means you actually have, hardware has to keep track of when it was last touched up. Right? It's pretty fascinating stuff. But it's pretty complicated. And then you load it up and you're done. Boom. Writing. Now, writing is very tricky, and I'm not going to spend very much time on this, but be aware that if you really get down into the nitty-gritty of writing concurrent software, you're going to have to deal with this. Because some caches are per core and some caches are shared. And whenever a core writes a number, they write it into the cache that is closest to it. And then the hardware will not typically write it out immediately, because that would be too expensive. That would mean that you would have to sync up all the caches, that if the same line is in multiple L1 caches that sit in, that belong to, that sit on L1 caches of different cores, they would all have to be synced up. If one of them touches it, it has to go out and then come back in. That's complicated. Hardware cannot do that. So hardware, typically there's a policy about writing how soon this happens. Pretty complicated, a lot of stuff happening behind. Bottom line, this is done for you. But sometimes you have to know how it's done. I'm not going to talk about cache associativity. It's something you may rarely stumble into if the access patterns in your application are such that you're always evicting lines. You may realize, okay, maybe my algorithm is just unlucky and it's running into this problem. Is there a way to, I guess, share these slides? Yeah, there's obviously no need to write down anything. You'll have a copy of this presentation in PDF form. So, basically, these are words to look for, to Google, if you're interested in learning more. All right, virtual memory. Again, I'm not going to spend too much on this. Bottom line is, whenever the operating system, whenever your application sees memory, it actually doesn't have view of the real memory. What it sees is the view of the memory that the operating system provides to this application, to your application. And it really is the view called virtual memory. Basically, think of it as a bunch of cache lines, and then these lines are organized into pages, so a bunch of pages, virtual pages. And then, whenever your application says, I need this page, I need to read this page, it's the OS's job to figure out where that page actually is. And in practice, it may be either in physical memory somewhere, or it's on disk, or it doesn't even exist and it needs to be created. Okay? Now, there's a mechanism for figuring out how to bring in a page, and it's called the address translation. There's a basically similar idea to the, instead of tags, we have the page indices, and there's a buffer associated with it, and whenever you don't find the page sitting in the main memory, there's a so-called page fault. OS will actually search the page table, and if it needs to bring it to disk, the OS will actually do that for you. Bottom line is, you don't want to involve this guy. You really don't want to involve this guy. So avoid page faults, well, except for when they're unavoidable, which means you're actually touching memory that has not been touched yet. But if your application uses more memory than the physical memory has, just stop. You don't want to do that. Because once OS gets involved with this, things just slow down to a halt. Okay? So that's all you pretty much need to know about this. That there is virtual memory, that data exchange in virtual memory, the unit of virtual memory is an actual, it's a page, and it's about 4 kilobytes. Depends on the system. But bottom line is, you don't want to deal with disk. All right, so summary, memory. The memory access is the primary bottleneck, and it's becoming more and more so because the computers become faster, and there are many more of them. There are many more execution units. But the memory is the coordination device for them. In order for you to synchronize, sort of to organize the computation that spans multiple cores, you have to deal with memory. And some algorithms are going to be inherently memory bandwidth limited. For example, sparse matrix algebra. Now, if you do dense matrix algebra, we're going to see later on today that it's on the edge. It's just right ratio between the memory bandwidth and the compute bandwidth that we have, that it's not hitting the memory bottleneck. But even that can actually be limited by the memory bandwidth. So how to deal with the memory bandwidth issue? Well, you want to minimize the amount of memory algorithm uses. A lot of times there are different ways of solving the same problem. Think, CI versus coupled cluster. I mean, they're solving the same problem. In one way, you have more parameters that you need in order to span the solution than in the other. Well, this basically says choose the algorithm where you compress as much information into the least amount of memory. So some algorithms are going to be more efficient than others simply because they more efficiently encode the data. They need less data. Best, of course, if all your data fits into the caches because they have relatively low latency. You want to maximize the reuse. How do you do that? Well, stride one access. So remember I said you don't want to access a single number from some random memory location and never use anything around it. Okay? The natural way for algorithm to minimize that is to use so-called stride one access, where you access elements that are next to one another. So then the cache structure becomes your friend. Okay? But if you can enhance register reuse, then you want to do that. You do not want to rely on virtual memory mechanism. Bottom line, this means manage your total memory that your application uses, and do not use more than the physical amount that is actually in your machine. So you want to know how much that is. Okay, adjacent instructions should access adjacent memory locations. That's, again, because of the cache language. All right. What time do we normally do coffee break? 10:30? 10:30. Okay. So let's hang in for half an hour more. Let's talk about now execution units. Now, why does that matter? Well, it turns out that certain types of operations take a lot longer to process than others. Okay, so you want to know which ones are the best and which ones are the worst. And a lot of times, you will actually choose one algorithm versus the other because, for example, the number of divisions is minimized. Divisions are particularly slow. So the parts of the CPU that actually do the operation is actually a relatively small part of the CPU. We'll actually see the snapshots of the silicon dies. And you'll see that most of the transistors are not spent here, not spent on ALUs, but actually all the machinery around. But that's where the actual instructions are executed. So you're typically going to have two types of units, well, sometimes more. You'll have an integer unit that is going to be solely responsible for integer operations. And it's going to be its own thing, so therefore Whenever you're using floating point units, this guy is standing around, it may be wasted. And sometimes it will actually manage the memory access. Depends on the architecture. Floating point unit does its own thing. It only acts on the floats. Whenever you have an expression where, for example, you have an integer plus a double, which one of them is going to be handling that?
Floating point.
Floating point. Why? Well, actually what's going to happen is there's going to be a conversion from an integer. Typically it's going to be done in the hardware, although maybe some compilers will do it in software, but I'm not really sure. Depending on what that integer is, it's a constant that is just going to cast it. The bottom line is it's going to be floating point unit that's doing it. If you do too many conversions, well, maybe you want to change your code a little bit. Sometimes often you're going to have separate units for scalar and simple processing. You'll see that. All right, here are the important things. Instruction latencies. These are very important because they can vary dramatically. Now again, latency is not the same as throughput though, right? But latency is an important one. So let's talk about latency first. Adds for the integers, I mean, that's just like the simplest bitwise operation. So add takes one latency. Bit shift is also, so anything that can be viewed as in binary, very simple, it's going to be very efficient. Division, it's pretty expensive. Expensive as in it takes a long time for the result to become available. Floating point units, here addition and multiplications, they're pretty efficient obviously because those are important operations. You cannot do floating point adds and multiplies. You really can't do too many things. Division is expensive and square root is expensive. Okay, so if your code does a lot of divisions, maybe you want to pre-compute certain quantities and recast it as a multiplication and so on. The reason why these take so long is that actually, essentially, the hardware validates series for you. These things have to be implemented in terms of sort of elementary things. And these are more elementary than these. So typically division and square root, you're going to have some power series expansion, maybe some interpolation table built in somewhere. So quite a bit of, again, sophisticated stuff happening down there. Bottom line, avoid division, square root, do everything with multiplies and adds. Okay, pipeline. This is how these things, how latency that is greater than 1 actually may be hidden. Okay? So you'd look at this and you'd say, oh my gosh, the latency, it takes 3 cycles for the result to become available. Does it mean that whenever that instruction comes in, my processor is busy, my floating point unit is busy for 3 cycles doing that? No, because that instruction is never really a single thing. And never a single instruction. There are multiple steps underneath it. And what happens underneath is an actual pipeline execution. So think of this as if we had a single execution unit and we had 4 cycle latency instructions in a loop, then this shows that we have, these are cycles basically, with clock ticking. We have the first instruction executed in 4 cycles, then the second instruction executed in 4 cycles, and so on. So throughput in this case is 1/4 of instruction per clock cycle. And that's not very good. Now, if you split up these instructions into sub-instructions, in other words, you can view an instruction as a decoding step, reading in data step, an executing step, and then writing the result step. Those, you can think of that as sub-steps of a single instruction. And then separate the parts on the silicon that actually execute those subparts, then you can set up a pipeline. It's basically like a conveyor at a car factory. So execution unit part 1 is going to pick up the first part of that instruction, evaluate it, and then pass on the results to execution unit 2. And pick up the execution unit 1 part of the next instruction. And so this way, by chopping the instruction into enough sub-steps, in this case 4, we can get a perfect 1 instruction per clock cycle throughput for an instruction that has a latency of 4. So latency is not end all be all. Latency can be hidden if you have some parallelism, if you have enough work to hide it. Okay, that's important. Now this pipelining clearly happens within the hardware, but the same idea is actually going to apply when you talk about parallelism. In general, you will want to generate more work and execute multiple units of work at the same time, so that the latency of each unit of work can be hidden in this similar fashion. I mean, the idea is as old as car manufacturer, I guess, or maybe even older. Right? So benefits of pipelining. Increase the throughput by recovering instruction-level parallelism. Basically, now we're executing a single instruction in parallel using 4 different pieces of hardware. Now, they're not identical. They do different parts of that instruction. Nevertheless, this is what we call instruction-level parallelism. And it's very important for making your code appear to run really fast, even though latency of each thing is pretty high. Each subunit here is actually simpler to build because it's simpler, right? It's not a cohesive unit. It only needs to click every cycle, and so it can run at higher clock speed. And so there was a way that actually in the 80s and 90s, the speed would double up every 2 years. Basically, shrinkage of the transistors plus increasing the length of the pipeline and extracting more and more parallelism out of each instruction. Okay, now here's a problem. Once you set up a pipeline, let's say we have a pipeline making cars, and then a guy somewhere in the middle gets sick. Okay, the pipeline stalled. Okay, now what gets sick in computer is, let's say someone is executing this unit, executing this piece of instruction, and then realizes, oh wait, I need some additional data. I have to wait for that data. The entire thing stalls. Everyone stalls, not just him, but everyone. So by organizing this pipelining, you're actually increasing dependency of the units on one another. And so that means that certain things become dangerous. Particularly dangerous are branches. So let's think about how these executions are actually, how instructions are executed. So what are these units? As I mentioned, think of sub-instructions as part of an instruction, being fetching an instruction is the first part, decoding an instruction, which means taking, a byte or 2 of the actual instruction value and looking up in the table somewhere and saying, aha, this is a code for an add, or this is a code for a multiply, or this is a code for something else. Okay? So that actually involves looking up data somewhere in the silicon and takes time. Okay, so decoding is complicated. Fetching data, that's the next step. Now that we understand what we're doing, whether it's an add or a multiply, we can start fetching data, even though fetching actually can be reordered and start earlier. Execute instruction and write result back. Okay, so you have at least 5 things here, but in practice, pipelines are going to be longer than this. Now, again, any of these can block the pipeline, can stall the pipeline. Particularly difficult are instructions that are conditional. Anytime you have a branch, which means in C or Fortran, if you have an if statement or for statement or a while statement or do statement, anywhere where you have a comparison and the next instruction to be executed depends on the result of that comparison, you may have a stall. Because until that result is evaluated, we cannot start executing the next instruction. We don't know what that next instruction is. Now, you're lucky that people have spent, really smart people spent a lot of time figuring out this problem. And the solution to this is an extremely clever technique called speculative execution. You have a piece of silicon that keeps track of the recent history of branches in your program. It's called, well, branch predictor has basically a cache. And it says, aha, this if statement, out of last 10 times I encountered it, every single time it yielded true. It will use heuristic algorithm to use that least recent history to figure out what is likely to happen next. And you'd be surprised how good these things are. So whenever I say, yeah, if statements are trouble, most of the time they're actually not because of the branch predictor. As long as the pattern of taking or not taking the branch is regular. If it's completely random, then okay, branch predictor is not going to do anything. But if there is some pattern, let's say every third iteration, if yields true, if condition yields true, and then it's going to be able to pick up that pattern. So it's really fascinating stuff. So basically, it will consult the branch predictor unit if there is a branch instruction, and it will figure out probability for taking the branch or not, and it will take the most likely probability and will continue executing as if without even knowing the result. Now what happens is, if it mispredicts, it actually has to unroll back the stack, so it has to basically stall the pipeline for real now and undo things, but as long as branch prediction is good, you can continue as if there was no branch. I mean, as if branch had no penalty whatsoever. Also, there is out-of-order execution. Again, hardware will not execute things the way they're written. Basically, think of it as you have instructions coming in, it chops each up into sub-instructions, and then it will figure out how it can reorder things in such a way that it can execute them maybe in parallel with them. Really cool stuff. Bottom line, the reason why modern CPUs are so good at running general purpose code are primarily these two things. Well, besides other things like, transistor, fabs, and so on. Anyway, so bottom line, there's quite a bit of stuff happening underneath the core, and you need to be aware of some of it. Most important, avoid bad instructions, avoid branches, even though, as I said, they're not going to be as big of an issue. And try to have code that has as few data dependencies as possible, because data dependencies can kill you. So let's talk a little bit about multiple issue or superscalar processors, because basically now we're going to actually see what the real processors look like and how many units they have. So far I've been talking about execution units and abstract. There's a floating point one, integer one, and so on. Well, here it is a real Intel Pentium Pro. This is like a real old machine back in the late 90s, I think. Pentium Pro. Okay, so the instructions are coming in this way, and there's a little pool called reservation station that holds them in, and then it decides which way they need to go. There's one floating point unit here, and then you have integer unit, 2 of them. Now these ports here, think of them, only one of them can be involved at the same time. If it says port 0 here and port 0 here, either there's an instruction coming to this guy or this guy. So it's clear from this picture is that you can, in principle, do an integer instruction and a floating point instruction at the same time, every cycle. Or you could do 2 integer instructions, although they're a little bit specialized, but that's the idea. You have multiple instructions being issued from the reservation station through these ports, and so if you have a good mix of instructions, your code is going to be able to take advantage of it. If all your code does is say floating point calculations, and your processor has an integer unit and a floating point unit, only the floating point unit is being utilized. Now, maybe that's what you want. I mean, some of it is just unavoidable. Let's say if you're dealing with graph algorithms, it's going to be primarily integer type operations. Obviously, in what we do, we'll primarily use floating point units, so that's what matters to us. But it really depends on your algorithm, and that means you need to be aware of what your processor is capable of. So in a code like this, for example, this instruction and this instruction can be executed at the same time. Notice there are no data dependencies, so they can truly be executed at the same time. Imagine this instruction here, instead of I, had a D. That would mean that until this instruction is executed, we cannot start executing this instruction. That prevents the parallelism. So the general idea of parallelism, again, chop up, create as many tasks as possible, make sure they have good instructions in them, and they're not dependent on one another. That's the best way. We'll see concrete examples of it. All right, let's move closer to what we do nowadays. This is a core. This is still an old machine, but now it has vector, arithmetic logic units, and scalar. Remember I said, SIMD type instructions and scale instructions are executed separately. Well, there are separate pieces of silicon that actually do that. The reason this guy is here is because obviously we do need to be able to run scalar code. All the old code on 8086 was scalar, so we still need this guy. But if you want to take advantage of the full capability of the processor, you better involve this unit. Okay, SIMD unit. Summary. Avoid expensive operations, division and square root. For example, sometimes when you need to divide by a constant within a loop, what you can do is instead pre-compute the inverse of that constant and then multiply by the inverse rather than divide every time. Now, a smart compiler may be able to recognize this, since maybe D doesn't depend here, but it may not because of aliasing, for example. This is a double array, and this is a double, may not know that. All right, avoid branches. If you can do that, at least inside the time-consuming parts of the code, if possible. Avoid data dependencies, especially between instructions that are next to one another, if possible. And avoid code composed of one type of instruction, but there is not much you can do about this. But if there is a choice, then yes, do that. Okay, a little bit about data parallelism. We'll have 10 minutes. So remember, in the very beginning, I talked about the SIMD model, the data parallel execution model, where basically each instruction acts on multiple sets of data. The reason for doing vectorization is engineers realize they simply cannot feed enough instructions into the core and decode them and execute them. So let's look at a concrete piece of code. Let's say we have a vector type operation. So A, B, and C are arrays of, let's say, doubles or ints, whatever it is. And we know their size, so we have a fixed size loop here that basically takes elements of the arrays, multiplies them, and stores them in C. Okay, so what's going to happen in vectorized code is instead of running this loop and within each iteration of the loop acting on a single number or a single pair of numbers, you're going to act on a set of numbers, and it's going to be represented by actual vector registers. Vector registers are going to hold multiple numbers in them. A scalar register, let's say, is going to have one double in it. An SEC2 type vector register is going to have two doubles in it. An AVX, those acronyms will show up later. Oh, actually, they do show up here. Most of your machines are going to be either, well, if you have x86, the SIMD operations or SIMD extensions to them are called SEC, SSE, or AVX. AVX is the more recent one, the advanced vector extensions. Then there's also AVX2. The difference between them is how many elements there are in the vector, plus the instructions itself. Why is it important? The longer the vectors are means the more data need to be held together. And your algorithm needs to be designed in such a way that vectorization can happen either by the compiler or by you. So this is how I would do this by hand. I would say, let's say I have vectors that are 32 elements long. Now 32 elements, that's quite long, but actually that's what GPUs do. Essentially think of GPUs as SIMD machines. They pretend like they're not, but they are underneath. They have vector registers that are 16 elements long, or 32, depending on which precision you're talking about. So this would be a GPU-like code, if the GPUs accepted this type of code. Notice I iterate now this loop not in units of 1, but in units of 32. In each iteration of the loop, I load up 32 adjacent numbers into one vector register and into another, and then I do a vector instruction. The processor is going to be able to do this very efficiently. And then I store it, and that's my vector loop. Now, compiler, most of the time, is going to be able to turn this loop into this loop, if it's this simple. If you have good tight loops, but a lot of times compiler needs help. So you need to be aware of vectorization. So benefits of it. Notice that now there's only one instruction, well, besides these loads and stores, that were still there, that need to be decoded. That means less hardware is going to be spent. Less power is going to be spent executing these instructions, and less hardware is needed. Because the data access is regular by default, by the model itself, we're acting on adjacent memory locations, then this perfectly maps onto the cache idea, the idea of cache lines and locality that imposes on us. Simple loops are going to be easy to auto-vectorize by the compiler, but don't give them too much credit. Compilers are notoriously bad at this. Unfortunately, not all vector operations can be, not all operations can be expressed in vector form. Sometimes you have dependencies in the data that prevent this. It's actually just hard to do. I mean, modern machines, well, modern codes, I would say, there's no vectorized integral code, for example. I don't think any of them generate too many SEC instructions. So it can be a lot of work. But basically, nowadays, that's the name of the game. In order for your code to run well, you either use a library that has code that uses vector instructions and vector units of the processor, or you write code yourself that uses these specialized instructions. You make sure that you vectorize your code. Okay, so these are the SIMD instruction sets that I mentioned. So streaming and SIMD extensions, they've been around for a while. Since SEC2, they actually have been, they've been applicable to double precision real numbers, and that's essentially our bread and butter. You only have 16 registers that you have, and basically they're pretty simple. Now AVX, they're better. They're longer vectors. It's more efficient. You're going to have some fused multiply add instructions, and as long as you have Intel St. Bridge, you already have AVX. Unfortunately, Hopi Speed actually doesn't have processors with AVX available. So if you want to try out AVX, use your laptop. And future SIMD extensions are going to involve longer and longer vectors. This is not going away. So if your code only runs scalar instructions and not vector instructions, and the processor, in order for full performance, requires you to use instructions that have, for example, sets of 16 numbers in them. You're essentially running at 1/16 speed on the peak. That's 6% at best, right? Because no code is perfect. So this is really important. Again, this is really important. GPUs can be thought of as SIMD machines, essentially. If It takes a lot of time, a lot of effort to rewrite code for GPUs. Well, primarily because of this reason, because you have to rethink your algorithms. All right, there are basically SIMD instructions on other architectures. Even, let's say, Samsung tablet is going to have Neon engine on it, and that's essentially a SIMD unit for doing something like graphics on a tablet and so on. So it's basically going to be everywhere. It's the name of the game nowadays.